When it's June the 10th. Alright, let's take a look. Maximum value at a given index and a bounded array. You're given 3 positive integers, n index and max sum. You want to construct an array nums that satisfy the following conditions. Num's length is n. Num's I is a positive integer where 0 smaller equal to I smaller than n. An absolute value of adjacent ones is smaller than 1, where I is in between, okay? The sum of all the elements of nums does not exceed the max sum. Nums index is maximized. Return nums index of the constructed array. Okay, so we need to build an array of size n where the adjacent cannot differ by more than 1. And we need a sum cannot exceed max sum. And every single value needs to be maximized. No, not every single value, as num's index is maximized. Very interesting. Very interesting. What it's saying is, given an array of size 4, right? Everything is positive, okay? And adjacent ones must be 1 or 0. And we have the sum does not exceed the max sum, and we want num index 0, 1, 2. So this is the one we want to maximize. And we want a total sum to not be 6, not be larger than 6. And we want to know what this value is. I mean, if we know a value here, can we figure out the rest? We want this to be maximized. It cannot be more than 6. So I'm actually thinking about binary search, right? If we set the max sum to, because it has to be a positive value, so the maximum has to be from 1 to max sum to 6, right? So if we do this, 7 divided by 2 equals 3. So we can say, okay, if I set it to be 3, can we make it? So if it's a 3, then we need the sum to be smaller than 6, right? If we can make it smaller than 6, we can make it even bigger. But if we cannot, then we have to make it smaller. So we need to find the minimum sum that's possible for this. And to find the minimum sum, we want to decrease, right? So we want this to be 2, this to be 2, this to be 1. This is the smallest we can get, right? So this one added together is 8. And it's larger than 6, which means 3 is not possible. So we need to find between 1 to 3. Then we get 2. So we add 2. If we get 2, we also try to get the smallest, but we cannot be 0. So it has to be 1. And this gives us 1, 2, 3, 4, 5. So this is good, right? Which means 2 is good, so we can try again. So between 2 and 3, right? Between 2 and 3, we get 2 again. I mean, basically, no. We got 2, right? And 2 is good. So next one we should do low plus 1. So it'll be 3, and then we'll get out. So low will be 3. So it's actually be this one minus 1. Okay, so I think binary search will work. So all we need to do is we find the middle value, right? And then we find out the first value that can be and the last value it can be. And then we can compute the sum. How do we find the first and last value? So we're here. Let's say we have a k in the middle, okay? Then I need to know what's the first one, then depending on your index, right? On your index. So, and this has to be, it also depends, right? It depends on when you hit 1, right? When you hit 1. So, no, we should just get to the first position. Now, where the first position going to be? And the first position is a positive, and then we just add them together. Same on the other side. If the first position is going to be negative, then we have a problem. Now we just have to fill them with 1. Let's just find where 1 will be. So whatever the index, 1 is just going to be like this is 3. So move 1, move 2, minus 2, right? So if it's k, it's just going to be index, whatever the index is, minus k minus 1. Here index is 2, okay? And k is 3. 3 minus 1 is 2. So this tells you at the 0 position we got a 1, which is good. If it's a negative, then we don't get 1. If it's a positive, like in this case, 2 minus 2 minus 1 is 1. 2 minus 1 is 1. So we'll hit 1 at position 1. So whatever is, okay, so that's that. And then we do the same thing on the other side. Okay, binary search it is. I'm going to pistas right. All right, so what do? We say low, high equal to 1. High has to be, let's do max sum. While low is smaller than high, mid is low and high divided by 2. Now we want to know the sum, right? We want to know the sum and to see if the sum can be, the smallest sum will be max sum. How do we find the smallest sum? Well, we find the smallest sum by find out the index. So index mean val index left, right, shall be your hold on, what's that? Index minus, so index minus your mid minus 1. Okay, and then mean val index right. Okay, now we'll handle the right. So if on the right, same thing, we go 1, 2, right? So it's gonna be your index plus k minus 1, right? Plus k minus 1. Yes, index plus mid minus 1. Okay. Then we are going to figure out what we are going to do, and then we say the minimum sum. So mean sum shall equal to 0, right? And then we have this left. Then we say if mean val index left is smaller than 0, smaller equal to 0, right? If it's smaller equal to 0, then we can do the full sum. Then we can say min sum plus equal to, what is the full sum? Well, the full sum is going to be mid plus mid minus, right, mid and index. Index is 2, so minus index, right, times how many items? Index plus 1 divided by 2. Else, if it's else, okay, then min sum will plus equal to from 1, right? So it will be mid plus 1 times something divided by 2. What is the something? The total count. Well, the count will be mid, right? Because we go all the way down to 1, and whatever the mid is, that's the total count. So yeah, so times mid divided by 2, and plus whatever is all the ones on the left hand side, because the value is positive. So all the ones. So how many ones do we have? Well, we have min value index left, right? This is where 1 is, and to the left of it, right? To the left of it. So it's just plus that. So that's that. Now we're gonna do on the right hand side, okay? So on the right hand side, we can say if min value right, if it's extend beyond, let's say if it's larger or equal to n minus 1, right? It's beyond, then it's just going to be the total sum on the right hand side up until the end, right? Up until the end. So we say min sum plus equal to from mid to what? So it's going to be mid plus all the way to the end. So how many do we have? Well, in this case, oh, it's going to be minus, my bad. It's going to be minus. Right? And the total is n minus 1 minus this. N minus 1 minus the index is the total number. Right, n minus 1. So it's n minus 1 minus index. That is the total number. We need to move to the right. And that's also a total number, mid minus. So this times the total number. What is the total number? Well, I mean, obviously we shouldn't add the mid again, so we should just do mid minus 1 plus mid minus this, and times the total, which is n minus 1 minus index. Right, n minus 1 minus index is the total on the right hand side, and this divided by 2. Else, if it's smaller, then min sum plus equal to mid minus 1 plus 1 times the total count. What is the total count? Well, the total count is going to be mid minus 1 divided by 2 plus whatever is the left on the right hand side, right? So shall be n minus 1 minus min value index right. Right? That's the total number. Yeah, so we do that. So once we've done it, we have the min sum. And we say if min sum is larger than max sum, right? If it's too much, then that means it's not possible. So we need to move the high into mid. It's too big. Else low equals mid plus 1. It's possible, so we can try a little bit more. And when we're done, we're gonna return low minus 1. All right, let's try this. 4, 2, 6, 2, 6, 1, 10, 3. Let's see if it's right. And index max sum. Okay, looks positive. I'll just give it a shot. Oh my god. It has happened more often these days. It just didn't work. Output 20, expect 24. Edge case. This is an edge case because we have the position being on 0. 1, 0. What's 1, 0? Damn it. We have 1, 0. Which means we have 1. And we want this position to be the largest. Yep, that is 24. And our scheme doesn't work. Oh, I never think we can hit. There we go. Yeah, I never think we can hit max sum, but I guess we can hit max sum. There we go. Yeah, that's just binary search. And you have to, yeah, that was a edge case I didn't consider. To use binary search, right? Pick a max value for num's index and then compute the minimum sum of nums possible. The main sum is achieved by always decreasing the values in nums from nums index to both sides. If the main sum is still larger than max sum, that means the current pick is not going to work. We need to reduce it. Otherwise, we can try increase it. The final pick that exits binary search is 1 larger than the correct solution. One edge case is that the high, the starting high has to be max sum plus 1, because it is possible that the answer itself is max sum. Okay, check this. Greedy and binary search. Oh, do we also do greedy as well? That numbers to its left decrease 1 by 1. Yes. Yes. I would just write all the logic here, but yeah, I see the same thing, right? You see the same thing. Yeah, you see the same thing. This one's a little bit more complicated, but overall it is the same. And they also did a minus value, which means this is just, yeah, this is slightly different, but it's fine. That's fine. We know what we're doing, so. And this is the difference. They get the right to get minus, the left to be this, so you can do this. But I always like to go the left plus 1, so I just have to return the low minus 1. Oh, that's actually not right. This is log max. Yeah, I don't know why I said the other way. Yeah, it's max sum. Okay, so this one's done. We'll go back to this. I don't know. Give it a thought, but didn't really learn too much. We got this as TLE. So what I was thinking is maybe we can, did our other ones first. Take away all the zeros. And then for the remaining, we might be able to shrink down. But I don't know. I want to see the hints. What's this? Oh, it's binary search. It's the same thing. Binary search. Binary search. Dude, I was thinking about binary search, but didn't come up with anything. But yeah, when you see the minimal, maximum, like these type of things, most likely it's binary search. But anyway, how can we binary search this? I mean, the ideal is if we want to set a value, and we say that is the minimum maximum, which means that's the maximum, right? Then we need to find along the nums, p number of pairs, whose, if we can find p number of pairs, whose difference is all smaller than this, right? Then that means it's not good. So we need to shrink it. It's too big, right? We can shrink it. If nothing is, then we shall increase it. But that's not as in, like, how do we even search for this? How do we search for the k pairs? Yeah, I'm having trouble trying to search. All right, let's take a look. Yes, we can. I just used that. I just did that. It timed out. I just did that, but it timed out. No way. No way. Hold on. we have 5 away. Okay, are you saying we should do top down? We can do top down. Let's top down. Let's try top down. How do we top down? So we have index and remaining, right? Okay, so index and the remaining. How do we handle this? We have index is from some index down, right? And we say we have however many remaining pairs. We need n equals len nums. Okay. So if index with the one that's larger, it should always be infinite, right? So from index towards the end, we know the maximum p it can be. So if the remaining is larger than that, then that's infinite, because we cannot find that many. If it's smaller or equal to, then we shall be able to figure, right? And if index is larger, if index is equal to n, or we can say larger equal to n, that means we don't have any value, right? And the difference is 0, because that just means we can't find any pair. Okay, so that's what I think. If index is larger or equal to n, that we shall return 0. And then really, index larger or equal to n, we return 0. I think so. If remaining is equal to 0, return 0. If remaining is larger than, well, n minus index. That's the total number of values we have. And then we divide by 2 is the maximum number of pairs. So if it's larger than this, that shall return max dot infinite. Okay. Otherwise, for my current, I'll either take my index. Okay, I'll take myself. And I'll do this part first, which is the maximum of nums index plus 1 minus nums index. So this is, I take myself, and then it has to be dp index plus 2, right? Index plus 2. And rem minus 1. Or I don't take myself, then it's going to be dp index plus 1 and the remaining. So we shall return the minimum of these two. And we shall return dp starting from 0, and then we do p. But if this passes, then I'll be very pissed. I'll be as pissed as I can be. Yeah, of course these pass. You'll have no idea how pissed that will be. Yep, it's not working, which is good. Which is absolutely good. That means it doesn't work. I think they must have changed it. Okay, so maybe we can do some of your optimization. Yeah, this is TLE as well. Understandable. Okay, let's try the optimization. Try take away some of the duplicates without affecting the overall structure of the array. How are we going to do that? Well, we actually take a look at this. Oh my god, you cannot take a look at this. This is ridiculous. And what you're going to do, you will go through the whole thing and you will look for the values that are, we'll look through the values, okay? And if there's more than 4, if it's 4 or more, then we can take away until we have 3 left. Because I feel if we have 3 left, it's still difficult to say which one you want to take. Right? You might want to take the left half, you want to take the right half. It's possible. Because if you take that, then you're okay. So what you're saying? I'm saying is we have a counter. Nums. We want to find a maximum number of pairs we can make, and at the same time take out a realistic number of pairs. And I need counter again. Elements, I can use elements. Okay, so we do the counter, and then we can say the maximum number of pairs for k in actually we need to say for k in counter, and the max pairs equals 0. Okay, then for k in counters, if counter max pairs, we definitely do max pairs. So max pairs plus equal to counter k divided by 2. right? That's the max pair we want. And we will also take away some, such that the remaining will be 3, right? At most 3. So how do we do this? We can say if counter k is larger than 3, right? Then what we can do is max pairs, realistic pairs. Realistic pairs plus equal to counter k, right, minus 3. Now I shouldn't say minus 3. It's if you are even, then you should leave with 2, right? So no, I should say if this is larger than 3, okay, and if counter k is even, then our result should be minus 2 divided by 2, and counter k shall equal to 2. Else, then realistic shall be this minus 3, right? And now we're remaining 3 because we cannot remain in 1. Okay, so we go through this, right? We go through all this, and I would say if max pairs is already larger equal to p, then we just return 0, which means everybody can do this, right? Otherwise p minus equal to realistic pairs, and then we say sorted nums shall equal to sorted counter dot elements, and then actually I like to use this. I think this is more fun, cleaner, as people might say. Right, so we do this, we don't do any of this, and n will equal to sorted nums. Blah blah blah, n is fine, this is not going to be num, this is going to be sorted nums, right? And we'll return dp 0, because everybody was 0, so it's just 0 and p. Solution 3. Not sure if it's gonna work. We take away as much as we can. Nope. Then what? It's not going to be this way. It does say greedy or binary search. We tried greedy, but greedy doesn't work. I don't think greedy works. Otherwise, we would have already done. Actually, it'll be interesting to see if it helps at all. You know, this. We can print. Let's print max pairs. Just print max pairs. Don't do this. We'll just return. Doesn't matter. Return 1. I just want to see. I'm just curious. Only 3. You can only handle 3, so that's definitely not. Yeah, you're not simplifying at all. Okay, so you sort this thing, right? And then what? I mean, you're supposed to sort also based on, consecutive stuff, right? Consecutive stuff. And you're trying to see, but if you do that, hold on, so you get a value. Let's try binary search. If you get a value, then you want to know if it's possible that we have more than p pairs, smaller or equal to that. And you can binary search, right? Well, yeah, I mean, if all the pairs, including duplicates, okay? Including duplicates, if all the pairs all the pairs that does not have overlap, we can put it in, right? We can put it in, okay? So we can use index, and we sort, and if we include something, then we can now include the other. But how are you going to handle this? Right? How are you going to handle this? 1103. Because that was the problem we have. 1103. If we do, we can say difference is 0, index 0. Difference is 1, index 0. Difference is 0, index 1. Difference is 2, index 0, 1, 2 as 2, right? And if we sort this, that's going to be 0, 1, 1, 0, and 2, 2. How are you going to binary search? We can say, all right, the max value we can have is going to be just the maximum here. So the max value, we say, okay, let's try the max is 3. Minimum is going to be 0, right? So low, high will equal to 0, and let's get 4, right? And then we say, okay, the mid is going to be 2. So do we have, what's p? P is to do we, and then p is equal to 2. So do we have 2 pairs whose value is smaller or equal to 2? And of course you do this, we have 3 pairs, but there's actually not 3 pairs, because there are pairs that cannot coexist, right? There are pairs we cannot coexist. So how do we handle that? How do we handle the pair that do not coexist? We can binary search, and then we just pick out the one that do not coexist and find out how many. Because if we have 2 pairs that do not coexist, like pair 0, 1 and pair 1, 1, right? And this, then we can only include one of them. Okay, we can only include one of them. And we're already binary search, so we know if they're inside the same bunch, then it doesn't matter, right? No, it doesn't matter, because I just keep one, I can throw away the other. If I do like this, then one of them is already thrown away. So all we need to do is sort this thing, get the mid, binary search based on this, okay? And then we go from front to end and try to find how many we can include. That seems to be a viable solution. That actually seems to be a viable solution. Okay, let's not do this. Let's use binary search. Create, right, is sorted array of diffs, of minimum diffs, of diffs of between adjacent values. Right, we just get adjacent values. Then pick a max diff. Then binary search to find the range where all the diffs are smaller than max diff. Then go through that range to see if there can be at least p number of pairs. If there are, we can shrink the max diff. Otherwise, we cannot. So I can still do that. We just need to change this entire thing, and then we need binary search from bisect import bisect array. I just realized I didn't use bisect for the other problem, but this one we need. Okay, okie dokie. So we need to sum, we need to sort. Oh, there's a lot of sort. So we sort this first, and then we can say sorted diffs, right, equals for I in range len nums minus 1. Okay, then what do? We do nums I plus 1 minus nums I, and then we put I here. Then we say sorted this thing. Okay, now low high. Low is gonna be 0. Okay, high is gonna be, I don't know, max nums. Oh, I already sorted, so I can just say nums minus 1 plus 1. Okay, low and a high. While low smaller than high, mid is low plus high divided by 2. Okay, then what we're gonna do is index is gonna be bisect right, doesn't really matter. Sorted diffs and mid key equals lambda tuple 0. Right, so we do that. Then we get the index inside sorted diffs. Okay, so what if it's equal? Well, if it's not equal, then we have here, right? Then we just go through the entire range. If we have equal, we do allow equal, right? Then we, yeah, bisect right is perfect. Then we just need to see how many pairs. So seen equals a set, okay? For j in range all the way to index. So we have to go through every single one inside sorted diffs, right? And then we just count, right? We just count. And then we say if sorted diffs j, that's sorted diffs, so we will get this I equals sorted diffs j. Okay, then we say if, and then say num, right? Num pairs, so num pairs equals 0. We say if I is not in scene and I plus 1, right? Not in scene, then num pairs plus equal 1, and scene.add I, scene.add I'm plus 1. If one of them is in, then we cannot add this pair, right? So we just go through all this. If num pairs is larger than p, so we have more than p pairs that can do. Actually, larger equal to p, right? We have p pairs. Maybe if we shrink it, we still have p pairs. So if it's this, that means we can shrink. Then we say high equals mid. Else, we don't have even p pairs. That works. So that means the current mid is too small. So we need to get it bigger. So low equals mid plus 1. Right. So we go through this and then we'll return. So it's now good. So we go low will be mid plus 1. Right. Low equal mid plus 1. Now we try again. And I think we just return low. All right, let's try this. Still not working for this thing, huh? Dude, result is 4. That is ridiculous. Let's go sorted diffs. Let's see if it's right. Sorted diffs, that's correct. Okay. And the first mid is, let's say, print mid and num pairs. Mid is 2 and num pairs is 1. That is bonkers. What's the index? Mid index. Okay, mid index is 3. 0, 1, 2, 3. That's correct, right? So we go from the front and then sorted index, so it will be 0. And this is I. And I say I take. Oh, shoot. Yeah, that's still an issue because you take this. When you take this, 1, you do not take this nor this because you take 1, right? And you will take, so we want to maximize, right? We want to maximize, which means if we take 1, so we take 1 and we'll abandon the others. See, that's the same stuff. That's the same stuff. You can't just say, well, just take everything, right? You can't. You cannot. How do we remedy this? So we want to maximize the number of pairs. Now we have all of them. How do we maximize the number of pairs? Of course, if you have consecutives, right? Maybe there's some rules. If you have consecutives, right? A0, A1, A2, A3, okay? If you have consecutives, if you take the ones in the middle, then you're abandoning the ones on the outside. So you can only take 1. If you take the ones on the outside, you are maximizing, which means if you have bunch of values, consecutive values, if you take from here, compared to you take from here, well, I take from this, right? You see, you take from this, then you are abandoning this. You can't even take, you're abandoning this. But I mean, in this case, you can. But if it's 1, 2, 3, 4, 5, 6. If you take this, you take this. If you saw from here, take this, take this, take this. So it seems like the only thing that's affecting is it's 4. If you take this, then that's the end of the story. I mean 8. Right? If you do 8, if you take this, these two cannot take, and if you take this, these two cannot, then you can only take, you're supposed to be. Okay, so what you're saying, what we're saying is after you sort, we need to sort again. What? That is bonkers, man. That is bonkers. I mean, we can take we can do that. So basically we have the index, we know what they are, then we'll take all of them, sort again. Now we're going to sort based on their thing, based on their indices, and then we just go through the index, right? So I think I'm gonna sort it again. Sort it. Okay. This will be I then. We don't need this. For J in range index. Sorted diffs. Okay. J 1. Okay. Now that looks promising. I'm gonna try it. Last shot of today. Last shot of today. Let's see if this works. Oh, this might be it. Oh, holy guacamole. This one is it. Damn. That's pretty hard. That is pretty hard, but we did solve it. We solved it. Maybe we don't need to use seen, right? If we add this next one, because it's just getting bigger, right? So if the next one coming in and the previous one is one small, so maybe we don't even need to use seen. What we need is number of pairs used. If not used, or I minus 1 is not equal to used minus 1. Used dot append I. If len used then I don't even need binary search. I just start from the front. No, you do need binary search because you need to sort by this. Oh, okay, let's see. Now another tricky part, right? Another tricky part is to count the maximum number of pairs, right? In the range of all pairs whose diff are smaller than the max diff picked. To do so, we sort again based on the pairs, based on each pair's starting index, right? And count greedily. Check whether an index has been used before already. A list of indices of the list of starting indices of all pairs. Well, in login for this we have log max nums for sure times each round we have log, we have n log n. Okay. Let's hope this one can be slightly faster. Wait, hold on. Maybe I don't even need to do this. No, it'll be easier. So I have to compute both times. Okay, let's hope it will be faster because we don't have to do the set. Yep, slightly faster. Slightly. Okay, we're done with this, but now it's time to really check binary search. Seems like my binary search is not the way to go. Well, we'll deal with this tomorrow. Alright, I'll see you guys tomorrow. Adios.